Hi. So, in this chapter, we're going to begin discussing probability. And probability we discussed very briefly in chapter 1, where it's just the likelihood of an event occurring. And so, this looks different in many variations. And so, this chapter is essentially just a crash course on probability topics and formulas because really our goal is to use probability in a deeper sense when it comes to statistics and testing claims and our descriptive statistics. So in this chapter, it's kind of like we're going to run through a bunch of examples of probability, and then in chapter 4 and so on, we're going to see the real connection between this probability idea of probability with statistics and descriptive statistics and how researchers test their claims. So it's not always all gambling and fun, right? The chances of winning the lottery or the chances of um, the ball landing on my number in roulette. It's a lot deeper than we just see. Like probability when it comes to gaming is theoretical, but on a surface sense, because probability is really intended to really look deeper at certain cases and make meaningful statements regarding a population. Okay, so let's go ahead and start. Okay, and we're going to start with just the definition which we've seen before. So the probability is a measure of the likelihood a random phenomenon or chance or behavior. Probability describes the long-term proportion with which a certain outcome will occur. So then, in order to be able to determine an event, right, we need to be able to conduct an experiment. So the experiment is the planned operation, and an experiment in this case with probability is the process that can be repeated. And that's kind of like tossing a coin. I can't toss a coin once and it land on tails and say to the whole world, every time you toss a coin, it's going to land on tails. Well, I only tossed it once. So if I really wanted to make that statement, don't you think I should toss it quite a few more times to see whether or not if I toss a coin, it would land on tails rather than just once? So maybe how many times, right? Well, I don't know, like 50, right? And then I say, well, that's not good enough because how many coins are tossed in the world in like one day? And so you're like, well, 1,000,000. Okay, let's toss a coin 1,000,000, 100 million. So again, the experiment is going to be a planned process in which we want to repeat so that we have outcomes to determine the chance and the likelihood of an event occurring. Okay, so let's go ahead and start off with some terminology. The first thing is the law of large numbers. And the law of large numbers is exactly what I had just stated, right? So the number of repetitions of an experiment increases. The proportion with which a certain outcome observed gets closer and closer to the true probability of that outcome. So essentially, they're saying, well, if you toss a coin 50 times and you see the data and it lands on tails, you can make a statement that says, well, in general, if you toss a coin, it's going to land on tails. And then I say, well, I didn't toss a coin 50 times, I tossed a coin 100 million times, and I found the likeliness being tossed between a heads and a tails is heads. So which advice do we take? Well, we take the one with a lot more trials because the law of large numbers says if you do the experiment a large number of times, right? You keep doing it and doing it and doing it, you're getting closer and closer and closer to the true probability of that event occurring. You can't just do something once and say that event occurs all the time. You would do it a lot, like the chance of it raining. Well, it's going to rain a lot through our life. For a long time, it's been raining since the beginning of time. So I think that they have a good idea now of the probability or chances that it might rain. So we just want to be able to do an experiment so many times so we can actually attain like the true probability. How many times? I don't know. It's just really up to the experiment itself and the intent of the experiment. So the first thing we'll need is the sample space of the event occurring. And the sample space is just the collection of all possible outcomes. So if I tossed a coin, what are all the possible outcomes? Can I toss a coin and get a piece of gum? No, like those make sense. So what are the outcomes when I toss a coin? So for example, I'll just put here, like if I toss a coin, right, the only options is it landing on a tails or a heads. So that is the sample space of tossing a coin once. Okay, so the event is the any collection of outcomes from that probability experiment. So in this case, if I said, what is the event of tossing a tails once from tossing a coin once? Well, one time in there, and the same with heads, right? There's only one of each. So the event may consist of more one outcome. It just depends again on your experiment and the intent of the experiment. So we do denote event with the capital E, and we'll denote that quite a bit. Or if we're doing a specific example, sometimes I'll denote it by just the first letter of the word or something. Okay, so let's look at a six-sided die. Consider the probability experiment of rolling a single fair die. Identify the outcomes of the probability experiment and what is the sample space. And let's define the event E of rolling an odd number. Okay, let's go ahead. So there's a few things. Let's do the first thing is let's go ahead and define the sample space. So defining the sample space will define all the outcomes. So if I tossed a die once, what could it possibly land on? It could land on a 1, or the 2, or the 3, or the 4, or the 5, or the 6. Okay, and if I wanted to define the event of rolling an odd number, what would that look like? Well, in a six-sided die, what are the possible odd numbers it could land on if I tossed it once? Well, it would land on a 1, 3, or a 5. Okay. So sometimes the sample space is not so obvious, but we'll do our best to be able to determine what that is for the event. So basic probability is really this basic formula, and the more involved the event of that you are looking at or observing, the more involved this formula gets. But it really is just a simple fraction. The probability of any event occurring is the number of ways the event could occur over the total number of outcomes. And we will use this formula over and over again and always go back to this and build the probability from this formula. So let's visit the six-sided die one more time. Now let's say, what is the probability of rolling a 3? So what is the event? Well, I'm tossing the die, yes, but what is the actual event that I'm looking at? I'm looking at rolling a 3. So the probability that this event occurs is going to be the number of 3s in my sample space. So let me go ahead and copy down the sample space here. So how many 3s do you see in my sample space? Well, I only see 1. So the number of ways that I can roll a 3 over the total number of outcomes, well, that's going to be one way out of how many outcomes. So I only have 1 3, right, in my set. I don't want to write the number 3 because that's the actual event, right? So I only see a 3 once in my sample set. And so what are the total number of outcomes? How many different numbers can I roll when I roll a die? Well, I have 6 possible outcomes. So 1/6. So what this says is that if I roll a die 6 times, one time I should see a 3. So now let's go to the next one. What is the probability of rolling a number larger than 4? Well, what is the event? The event is rolling a number larger than 4. So the probability of the event occurring is the number of ways I could roll the number larger than 4 over total outcomes. Okay, so how many ways can I roll a number larger than 4? Well, larger than 4, does that include 4? Well, if I said, is 4 larger than 4? No, right? So anything larger than 4, which would be 5 or 6. How many outcomes is that? Don't look, say, well, 6. No, it's not. It's not. It's how many outcomes do you see? Right? 2. I see 2 outcomes that I could have tossed a die and get a number larger than 4 out of the total number of outcomes, which is 6. So reducing this is 1/3. So they're saying that if I roll a die 3 times, that I should see a number larger than 4 once. So now what is the probability of rolling an even number? So now you tell me what the event is. That's right, roll an even number. And so the probability of this event occurring is the number of ways to roll an even number all over the total outcomes. Okay, so now let's think about it. How do we roll an even number? Well, the sample set is 1 through 6, so even numbers would be 2, 4, 6. So how many of those do I have? I have 3 out of 6 outcomes, which is a half. So this means half of the time, like I should be tossing an even number, right? Which makes sense because half the numbers are even.